In this segment, I'm going to provide a brief overview of the different elements of the ANOVA table and their relationships with one another, specifically how variance is partitioned, and then I'm going to walk through some R output for a multiple regression, that is a regression with two or more predictors, and explain all of the details that are presented in that output. So definitely know these relationships. This ANOVA table is generated from SPSS, not R, and it is the same example that we've been working with from Andy Field, where we are trying to predict whether an album will sell well, will people buy it, based on a couple of predictors, the number of plays the album gets on the radio, and then the advertising budget for that album. Now, I like SPSS for a couple of reasons. First, the output that it generates is much prettier. It's in pretty tables, the decimals are lined up, it just really looks nice and it's easy to learn from. Whereas R generally gives us output that's not as pretty and organized. And I think there are apps to do a better job, but I don't know if there are apps that produce this nice of output that SPSS gives us. And if you find different packages in R that will produce output like this, let me know. At the time of this recording, I really haven't found too many yet that do. There are a couple that I think I'll introduce to you later on. But overall, I just like how SPSS is easy to learn from. It's easy for me to teach from. And a lot of times with the R output, I'm like making it pretty for you before you even see it. That's why what I am showing you on screencast sometimes looks different from when you run the analysis yourself and look at the output. The second thing is I like how the regression, sum of squares and mean squares, is all together. And what I mean by that is all the predictors are represented in this mean square and sum of squares. In R, conversely, the predictors are separated and they have their unique associated sum of squares. And so to get the sum of squares regression, you have to add all of those predictor sum of squares together and then divide by the K, or the numerator DF. And so that's a little bit more of a two-step process when we're trying to get the regression SS that we didn't have to worry about so much when we have other stat programs. Now, this is something to keep in mind when looking at output in an exam or with clients or whatever, knowing that the output can be presented in a couple of ways for regression. First, the regression sum of squares and mean squares are aggregated together across all the predictors, and then like R does it, separating them out. And I'll show you that here coming up later on in the screencast. But just know that there's going to be a little bit more math involved, adding things together when the regression sum of squares is divided up that way based on the predictors. So here are the different equations to know. Definitely know that the MS regression is equal to the sum of squares regression divided by the numerator DF, the number of predictors, the regression DF. All those mean the same thing. And note that sometimes the number of predictors is not denoted by K depending on the textbook. And so I think in Field it is a P actually. So don't let that confuse you. Different people refer to it in different ways. I know that it's difficult sometimes to keep it all straight, but I'm going to try to be very consistent and use K throughout the class. The MS residual is the SS residual divided by N minus K minus 1, and that's denoted here. We have the sum of squares is 480,427 something, and then that dividing that number by 197, I think, yeah, the total sample size is 200, so N minus K minus 1 is 197, and then when we divide this into this, we get this 2438. And then finally the F-test, very important. So knowing that it's the MS regression over MS residual, understanding that proportion, if one element like the denominator increases relative to the numerator, all else constant, increasing this denominator, what happens to the F value itself? this is extremely important to know. So understanding these things inside and out is going to make you extremely valuable in industry to clients and also when trying to publish research, and just knowing how to understand research in general and understanding what error is relative to the basically the part of the variability that is explained by our model. So all else constant, we want this MS regression to be large and this MS residual to be smaller, and understand why that is. Think through that proportion, and also for the MS residual, what does it look like if this denominator increases relative to the numerator? Does that make a larger or smaller overall MS residual? So think through those things, super important. So basically we have variance of a given DV partitioned into variance explained by the predictors in our model versus variance unexplained. And unexplained variance, again, is also referred to as residual, error, or just unexplained variability. I hear all these terms used interchangeably. So they all mean the same thing. Let's now walk through our output for a multiple regression. So as always, this is an embedded document, so do left click once, right click once, and then do an open. So we have, remember, the two kinds of output, the coefficients table, which gives us the B weights for the y-intercept, and then the two predictors. In this case, we're just going to work with 2. And the ANOVA table has the sum of the squares and all of that good stuff and the F values. So this is the code used to generate this table right here. And we're using this data set called faculty. It has an N size of 62. There are 62 faculty who reported their salary. And we're trying to predict faculty salary from the number of publications they put out, and also the number of years since they got their PhD. So those two things, can we predict how much money they make? And then for the ANOVA table, here's the source code for that one that you can get this. This is all, again, in the R code document as well. So you can see exactly how I did it and notes. I made a lot of comments in that document as well. All right, so back to our output here. Let's go through things one by one. So we have, first of all of the B weights for the y-intercept. Oh, by the way, these two predictors have meaningful 0 points, which means it's possible to have 0 publications and also be just graduated with your PhD. And so centering in this case is not as important. And unless otherwise indicated, I'm always going to work with uncentered data, just so you know. And so remember, the y-intercept in simple regression is when we want to see the expected value of the DV when the predictor is at 0. And in multiple regression, it's simply, what is our expected value of the DV when all predictors are set to 0? And so this $44,955 is the expected salary for a faculty member that we would see when the person has no publications and they have just graduated with their PhD. Right, so 44,900 something is like the starting point. And so I made a note of that here. And then for each B weight, now let's talk that through. This is super important. I'm going to expect that you can talk it through like I'm doing on an exam. For publication B weight, this is for every one publication, we can expect $133 increase in our yearly salary as a faculty member. So each publication's worth about $100, which is pretty sad. It's like, why would I ever publish? Except for prestige, and it's related to other things, but we can see that that is not significant. So its associated t-value is 1 point something, and then the significance, it just doesn't reach. But for years since graduating with our PhD, for every 1 year increase, we can expect to get $1,096 increase in our yearly salary. Right, so as we have 1 unit increase in years, or 1 year increase, we can expect the salary to go up by this much. And that's the level of thinking that I want to see displayed when we're talking through things, is that you're not just saying expected, what do we expect the DV to change when we increase by the predictor by 1? That's technically correct for a slope, but I want you to relate it to the constructs in the example, right? This is important because that means that you can apply what a B weight is in any context, and you can talk through it so that a client can understand it pretty well. All right, so I made notes on this, and then down here, remember, is the information about the model as a whole. And so the multiple R squared is 39.08% of the variability, and salary is explained by the optimally weighted combination of these two predictors. That's important to know. And this is a big effect size. So this effect size is rather large. Yeah, in reality, in most of our research, I would say, in industry and just in academia, publishing, we don't expect to see effect sizes quite this large. So this is data that came with an old textbook that I had. So it's a little bit, I don't know, maybe unrealistic. And it doesn't reflect, I don't think, real world effect sizes. So just know that in class we talk about these large effect sizes, and you can see they're very significant is not really accurate. They reach significance at a very low p-value. When you get some real world data, it's going to be a lot messier and the effect sizes will be a lot smaller, just so you know. There's going to be a little bit of divide with the data that you learn on and then the data that you're actually collecting for your dissertation, usually. Now, if you get lucky and you have a great intervention or IV manipulation, or you have a study that's correlational, non-experimental, you may get some nice effect sizes that are like this, but don't be surprised if you don't, I guess is my point. Now, the standard error of the estimate is located right here, $7,700 or something like that. And so that's interesting just to note. So you know this is the standard deviation of the distribution of residuals. So understand that, be able to articulate what that is. It's a measure of our poorness of fit. And then we have our associated F statistic here with our DF. We have two predictors. This is K, numerator DF, or regression DF, and then this is our denominator DF, or our residual DF, which is N minus K minus 1. And then the whole model is significant at this very low p-value. Now let's turn our attention to the ANOVA table. This is going to be a little bit of doing to try to explain, and part of the reason is, again, remember when I said that the regression sum of squares is going to be the pub sum of squares and year sum of squares. So adding those together, and I put that down here, will give us the SS regression. And that's going to be important because when I ask for the SS regression, then you know to add up all of the SS the sum of squares for each one of the predictors. And then the residuals is great because that doesn't require any calculation. It's just this amount right here, which is helpful. So let's work through this. So for the SS regression, again, adding the pub's SS and the year's SS, and that will give us the regression. So I'm repeating myself, my apologies. So I do that down here. Add it up, and this is salary, so these are huge numbers. It's kind of clunky to keep adding. By the way, during exams, I'm not going to ask you to add up a lot of numbers and then assign grades based on how well you calculate things. That's not how I work. I want you to know which numbers to plug in and what the formula is. And so if you simply, say these two numbers added together, I'm not going to ask for the final result. I'm just doing this for illustrative purposes for you. And so this is the number we get when we add those up. And then the MS regression is going to be the SS, remember regression, divided by K, which is the DF. And so I did that calculation here, and we end up with this as the MS regression. And then for the F test, we're going to do the MS regression over MS residual, and that's this one right here, the 59,000 something. And so when we divide that out, we have an F of 18.92, and that is the same as the one up here. So I love when it comes out exactly the same, really is helpful. All right, so that concludes the portion of the, this portion of understanding the output, understanding the various elements. We're going to go over the adjusted R-squared later on, so don't worry about that one. But I guess for now, focus on what makes a large F value versus what makes a small F value. What are the different pieces to, that go into that determine that. Understanding it mathematically, understanding from memory how to talk it through, just like I'm doing on an exam. All right. Hope that helps.